In this video, we'll start the solution of the hydrogen atom. This is one of the only three-dimensional potentials we can solve in closed form. We'll start by looking at the hydrogen atom potential, then developing the differential equation for the radial component and finding the asymptotic solutions. And then finally, putting it all together and generating an equation for the polynomial that mates the two asymptotic solutions. So the potential of the hydrogen atom is simply the Coulomb potential, which is a spherically symmetric potential. It only depends on r. And that is V of r is equal to minus e squared over 4 pi epsilon naught times 1 over r. We assume that the nucleus, that is the proton in this case, is stationary because it's much more massive than the electron. This is an approximation that will relax later on, but for the moment it allows us to solve this in a relatively simple closed form. We can now substitute this potential into the radial equation for U, which we developed in the last video. So minus h bar squared over 2m d squared u dr squared plus the quantity v of r plus h bar squared over 2m ll plus 1 over r squared all times u is equal to e sub e times u. Well, the potential is now the Coulomb potential. When we put that in, we get a minus e squared over 4 pi epsilon naught times 1 over r here. We now can divide by e and bring these terms all over to this side. So when we do that, we get minus h bar squared over 2me d squared u dr squared equals 1 from this term plus e squared over 4 pi epsilon naught capital E times 1 over r minus h bar squared over 2me L times L plus 1 over r squared all times u on the right side. We can now rewrite this with common terms. And the common terms are h bar squared over 2me, which appears both in the first term on the left side and the third term on the right side. But if we take these constants and pull out an h bar squared over 2me, we're left with me squared over 2 pi epsilon naught h bar squared. And now we have three terms all have the same constant in front. We're now going to make a substitution, the usual substitution, when we have the requirement that the energy is less than 0. This potential is minus v squared minus 1 over r, which means at the origin it goes to minus infinity, and at infinity it goes to 0. So any bound state will have an energy that's lower than 0. Because E is less than 0, then we can make the usual substitution for kappa, which is negative 2me over h bar squared, all square root. And the negative sign is inside the square root in order to make this positive definite. So in that case, the minus sign is incorporated here, a minus sign is added in here, and the minus sign is incorporated here. When we do that, we can now rewrite this equation in the following way. 1 over kappa squared times d squared u dr squared is equal to 1 minus me squared over 2 pi epsilon naught h bar squared kappa times 1 over kappa r, so there's a kappa squared there, plus L times L plus 1 over kappa r quantity squared times u. If you notice, what we've done here is we've grouped a kappa and an r together in all these cases. So here we have kappa r, here we have kappa r quantity squared, and here we have dr squared and a kappa squared along with it. Now we can substitute for kappa r with a new variable we'll call rho. So rho is equal to kappa r, and then we're going to take this constant which is left over and call it rho sub 0. Which is me squared over 2 pi epsilon naught h bar squared kappa. When we do that substitution, we get a nice simple equation that we can look at more carefully and solve. D squared u d rho squared is equal to 1 minus rho sub 0 over rho plus L times L plus 1 over rho squared, all times U. So in the same way as we solved the harmonic oscillator analytically, we'll start with the asymptotic solutions, because here we have a potential that grows very large at the origin, and with these three terms, and goes to 0 at infinity. So we'll start by looking at the rho goes to infinity. So when rho goes to infinity, the constant term dominates, because these terms drop off, and this term is now the biggest term left over. So this makes a very simple differential equation. D squared U d rho squared is approximately equal to U at infinity. In the solution, we know what that is. It's a real exponential. So we have U of rho is equal to rho, when rho goes to infinity, is equal to A e to the minus rho plus B e to the rho, right? Take the second derivative and you get the function back again. Well, as usual, we have the one solution which is unphysical, which is the one that explodes and is unbounded and non-normalizable at infinity. And so B is set to 0, and our solution then is A e to the minus rho. Now, when you look in the limit of rho goes to 0, this term, the centrifugal, so-called centrifugal term, L times L plus 1 over rho squared, is the one that dominates. So in that case, for rho going to 0, the solution has to satisfy this approximate differential equation. D squared U d rho squared is approximately equal to L times L plus 1 over rho squared times U. And we have, again, as usual, two solutions that solve this. These are polynomial solutions, because you can see when you take the derivative twice with respect to rho, then you reduce the power of rho in U by 2. And so this has a solution that looks like this. U of rho is equal to C times rho to the L plus 1 plus D over rho to the L. Well, you can easily see how this satisfies the equation, this approximate equation, by taking the first derivative and showing that when you take the first derivative of the first term, you get L plus 1 times C times rho to the L. So you reduce the power by 1, and you get an L plus 1. And when you take the derivative of the second term, you get a minus L from the rho to the L in the denominator, D over rho to the L plus 1. Take the second derivative, and you get L times L plus 1, C rho to the L minus 1, which now is a power that's 2 times lower than, or rho squared lower than the original function. And then here you have L times L plus 1 times D over rho to the L plus 2, which again is the power is reduced by a factor of 2. Again, this term blows up at 0 and is unphysical. And so we can set D equal to 0, and we get a solution that only contains the first term. So U of rho at rho goes to 0 is got to be approximately C times rho to the L plus 1 power. So now we have our full solution at the asymptotes. So the asymptotic portions are sandwiching some function in the middle, which makes sure that the two functions and the derivatives match up all the way through. The solution then is U of rho is equal to rho to the L plus 1, V of rho, e to the minus rho, where V of rho is now a polynomial in rho. So if we look at this solution, we can sort of see how this works. Let's first plot e to the minus rho in red, and then rho to the L plus 1 in these other colors. So if you just crudely add them up, you can see that what's going to happen is that the e to the minus rho will dominate out at large values of rho, and at low values of rho, the linear, quadratic, and cubic terms will dominate. And so it'll rise and then fall. If I simply add these together, I get the following curves. I add the row, e to the minus rho, to these, or multiply them together, and the function that you get looks something like this. So it has a peak and then drops off to 0. Starts at 0, has a peak, and drops off to 0. And the higher the value of L, the larger the peak, and the further out it is. So what we have to do now is to determine whatever polynomial will match up the derivatives in the first and the derivatives and the first derivative and the functions, and solve the full differential equation for u. This is done the same way as we did for the harmonic oscillator. So we start by substituting this solution, rho to the L plus 1 e to the minus rho v of rho, into the differential equation for u. That means we need the second derivative of this function. So that's where we start. We take the first derivative of u with respect to rho, and the first term gives me an L plus 1 times rho to the L e to the minus rho v. Then we take the derivative of the second part. We get minus rho to the L plus 1 e to the minus rho v. And then we take the derivative of the third one, which gives rho to the L plus 1 e to the minus rho dv d rho. We can now regroup this by pulling out a constant term, which is rho to the L e to the minus rho, a common term rather, and that is multiplied times L plus 1 minus rho, all times v, plus rho dv d rho. I now want to take the derivative of this to get the second derivative of u with respect to rho. Well, that's going to involve 1, 2, 3, 4, 5, 6 terms. So the first term is going to be L times rho to the L minus 1 e to the minus rho times the stuff in the square brackets, L plus 1 minus rho, all quantity, times v, plus rho times dv d rho. Then I take the derivative of the e to the minus rho, so I'm going to get a minus rho to the L e to the minus rho with the same stuff in the square brackets. Then I want to take the terms in the square brackets and take the derivative of these, and this is going to give me 4 terms. So I have in front rho to the L e to the minus rho, and I have minus v, because when I take the derivative of this, these terms go to 0. This gives me a minus 1, so I get minus v. Then I have this quantity, L plus 1 minus rho times dv d rho. Then I have another dv d rho when I take the derivative of rho. And finally, I have rho times d squared v d rho squared. Now, these terms can all be put together with a common term factored out in front. That is, we're going to factor out rho to the L e to the minus rho for all these terms. And the last two terms have them all, have these terms, these two factors in front. This one in the front has an L and a rho to the L minus 1. So what we need to do is put a rho, an additional rho here, and divide by rho in here. When we do that, we get rho to the L e to the minus rho. And then the first term is this one, rho times d squared v d rho squared. That's very clear. Then we're going to gather the terms with dv d rho. Well, I have a term here plus rho, and I have to divide by rho, so this is going to be dv d rho with a plus sign. This term here is minus rho times dv d rho. And this term here has a minus rho dv d rho and a plus dv d rho. And so I get 2 times L, this one had an L in front of it, plus 1 minus rho dv d rho. Right, so I had an L plus 1, I get another L here, I get another 1 here, and then I have 2 terms with rho dv d rho, this and this. And so that gives me these terms here. And then finally, I take the constant terms and I group them all together. And I get the constant terms are not the terms multiplied times v, and I get rho minus 2 times L plus 1 plus L times L plus 1 over rho times v. And that comes from this term with an L, and I get a L plus 1. Then this is minus 1, so I get an L. And then I have these terms here with the v, and then this term here with a v only. So this gives me the minus 1. All right. Now, if I now look at what I have my function, u of rho, and my second derivative, d squared u d rho squared, which we just worked out. I now want to put this into the Schrodinger equation, which is 0 is equal to d squared u d rho squared minus the quantity 1 minus rho sub 0 over rho plus L times L plus 1 over rho squared times u. And it's going to get very long, but it will simplify rather easily, into a very compact form. All right, so the first thing I'm going to do is I'm just going to put the function in for this value of u. So I'm going to get d squared u d rho squared minus 1 minus the quantity 1 minus rho 0 over rho plus LL times L plus 1 over rho squared, rho to the L plus 1, e to the minus rho times v. And then I have my second term, which is this. I'm just going to write it out. And remember, it has a common term in front, which is rho to the L, e to the minus rho, and then these three terms, which have d squared v, dv d rho, and then v. What I need to do now is put this term here on an equal footing. That is, I have to factor out a rho to the L, e to the minus rho. That's pretty straightforward. I have e to the minus rho, I have rho to the L, I'm left with a rho multiplying everything that's in here. And so when I do that, I get minus rho sub 0, that has canceled that, plus L times L plus 1 over rho, all times v. Well, this has to be equal to 0, so I can ignore the first factored out term, because the only way this can be 0 all the time is if the quantity in the braces is equal to 0. I then realize that this term can be pulled down completely. So it's rho d squared v d rho squared plus 2 times L plus 1 minus rho dv d rho. These are the terms with the second derivative and the first derivative of rho with respect v with respect to rho. Now the terms that just have a value of v, I can look carefully and I see that this term here and this term here will cancel because of the minus sign here. This term here and this term here will cancel because of the minus sign here. So I'm left with a plus rho 0 minus 2 times L plus 1 times v. And that's what I have. So it's rho 0 minus 2 times L plus 1 all times v. This is the equation that we have to solve for v, the polynomial that matches up both the two asymptotic solutions in function and derivative. We're going to solve this the same way as the harmonic oscillator, assuming that v of rho is an infinite polynomial in rho. And we can write that very simply. V of rho is equal to an infinite sum from j equals 0 to infinity, c sub j, rho sub j, rho to the jth power.